Hi, welcome back to my channel. This is another of my series on the Racket programming language, and today we're going to talk about the concept of streams in Racket. And streams are a way of defining a sequence of values that is generated on demand, in a sense. You can think of this as a natural example of, let's say I wanted to generate a list of every number from 1 to a billion, right? But I knew that I really was very unlikely going to use all those values, that I'd actually stop a computation way before I got to a billion. But in the worst case of things, I need to generate a billion things. Well, I couldn't just make a list with a billion things and then enumerate over them. I would have to kind of do what a for loop does, if you think about it. And what streams do in a functional programming language is they kind of allow for those for-like computations to be done in a much more functional-like way by basically mapping over a stream. And then that stream, since it generates values on demand, means that you're not having this huge explosion in space when all these possible values have been computed. And what this does is it makes for certain types of solutions, it makes it fairly easy for them to do in a functional sense, without having to kind of go back and either do them manually by doing recursion to kind of basically doing tail call recursion to emulate a loop. You can kind of think of it as a higher level. And the best way to kind of introduce this is to motivate it with an example. And recently I've been watching a little bit of Countdown on YouTube. And Countdown is a UK television program which has people kind of solve 3 different types of puzzles. 2 of them are based on letters. One is you choose a bunch of letters and then try to make the biggest word out of the letters that you've chosen. The second one is basically what they call conundrums, which is basically they've scrambled up a 9-letter word and you have to unscramble it. The third task is really the interesting one because it's basically a numbers game. And what it is that you can choose a set of what they call large numbers and a set of small numbers up to 6. And then you are given a target number from 100 to 999, and then your goal is to try to come as close to that number or exactly that number by using basic arithmetic operations on all the combinations of numbers to get that solution. So it's a really interesting problem from a computer science standpoint to think about how can I solve that, because it's one of those things where it's a very natural type of thing. We're used to doing numbers. And the more you look at it, it becomes very interesting how you can, is there any kind of structure you could exploit? I'll get back to that in a second. But, do you have to brute force this, or is there any way you can make this more optimal? The interesting thing about it is that there really isn't any way to brute force this. In the worst case, you have to just kind of go through all possible solutions. And there's 2 different ways of organizing that. One is to literally go back to what we did with binary trees and how that can represent arithmetic expressions. Literally what you do is you generate every possible binary tree up to 6 nodes. And you then just go off and one by one try to see if that tree can be solved to match the target. And so you're generating a large number of inserting things in this tree. And that actually can work fairly well if you just do some fairly careful optimizations on how you present those trees. There's a lot of people, what they do is they do solutions where you literally pre-compute that and you generate an enormous file that goes off and just basically does all these possible trees calculations. Each one of those possible trees is actually just a function. But we're going to do this a little bit differently. The other way you can kind of approach it is that what it comes down to is this literally is a combinatorics problem, where if you're given a certain set of numbers and a certain set of operations, how do you combine them all together to see if you can make that target? And if you do all the possible ones, you will eventually see if that's possible or not. And the fact is that it is, in some cases, impossible to meet the target. Therefore, you do have to exhaust the solution space. Then you ultimately have to kind of just write your program to do that. And so what it kind of comes down to is the way people think about the solution is they do something that's called reverse Polish notation. And reverse Polish notation comes from a mathematician called Pol. It's not really anything to do with the country Poland, but excuse me, not Pol, but his name's Polish. So it's a name of the mathematician that made it, not the country. But the idea is that you have a stack of numbers like this. So let's say you start out with a stack of numbers like 150 and 40, and then you do a set of, then you can put in a set of operations. So if I do a plus, what you do is you take the first two numbers off the stack, because plus expects two numbers, and then you perform the calculation and you push the result back on the stack, right? And then you could do another operation, let's say minus, take the two numbers off there, put the result of the operation back on the stack, right? If you think about it, what we can do to solve this problem is we can literally just go off and generate the following. Well, the first thing we can do is we can say, well, you know what? There's a trivial solution here. If the target number is in the list, right? So let's say if it's 100 and we have a list that has 125, well, that's a trivial solution. It's just in the list. The solution is the solution, just the target number. The next thing you can check is that given a list, given any two numbers, right, and any possible operation, is there something that equals that target? And again, you'd have to check every single combination of, every combination of two numbers from that list to do this. But then you can do that. Otherwise, you can go off and then you just kind of expand it. Is there anything that basically there's a list of three things and two operations, and they kind of the reverse Polish notation sense, that also it equals the target. And then it's so on and so forth. And then eventually what we do is you have to go up to the worst case, which is we have 6 numbers and then we have 5 operations. And we have to check all those possible permutations. And that's pretty large. That's a large amount of stuff. But again, if we're getting to the worst case, then, there's a good chance that maybe we'll find a solution way before that. And the trick would be is that if we had to generate, again, all these possible combinations and operations up front, only to reject like 96% of them, the program would be way too slow. But streams allow us to get away with this. And so what you can do here is this is the first example of how you can create a stream from a set of lists. And so there's this 4* here. And what this 4* is kind of a nested loop. So it will basically, for each operation, it'll go through each one of these subsets and then do this. And the thing about what's interesting is you can note that this is defined recursively. This works still. It knows how to handle this. And so this will literally generate a stream of all the potential combinations of operations up till, n. And of course, the thing about it is that we have to make sure we have the trivial recursive case. And here's the thing is that for n equals 1, we have four possible operators you can choose. And so we return our list of 4 here like this. Okay. And now what we do is we did what I said before about how we kind of solve this. We take this base case. Can you solve it in 1? Is there a number? Is the target in the numbers? Right? Just as easy as that. Basically is the target a member of numbers? If not, then it's false. Otherwise, you just return the target because we're done. Okay, and so every time we don't find a solution, we return false. And that's the whole point behind this, is that now if we have 2 numbers that can be combined to equal the target, we have a solution as well. And so now we just take the first and the second part of that list, and then we just do every possible computation on that. We add the 2, we subtract the 2, but in 2 different orders. We times the 2, and we only have to do that once because multiplication is, associative. It doesn't matter what order it's done in. And we do the things here is that we have x and y and divide y, x minus y, and divide y minus x. We do this check. Now this is actually technically not quite as good as it should be. We should be doing a check to make sure that x is not 0 here. But what we're doing is we're taking advantage of the fact that we know the structure here, and we know that basically if we're given a solution that has 0 in it, that actually isn't a valid state of the game, so that would never happen. The proper thing to do, of course, would be to do that check or to document it, but that's why we have this kind of shortcut. And again, that's not best practice. That tends to be the kind of thing that really will trip up programmers, is that when those kind of checks are left off because of the structure of the data, and you don't document that can really cause for some confusion. Now, I'm going to do 2 things here, so I'm going to ignore this for now. And then what I'm actually do is I'm going to say, okay, in this general case, I want to do the following. I want to create a thing that solves an RPN where I have a list of operations and I have a set of numbers and I treat it as a stack. And this is really it. And so the base case here is that if I only have one number on the stack, then that's it. I'm done. Just return that as the result of that solution. And what we're doing here is it doesn't really matter if we have a bunch of operations left because we don't have anything to operate on, and that would be the end of it. Now, of course, this is a specific case here because we're only doing plus, minus, adds, and multiplies and divides, and we don't have what we call unary operations, like we wouldn't do the negative number. This is why you can get away with doing this and ignoring the operations here. It'd be an interesting exercise to say, oh, if you want to treat minus as a unary function, how this would work, and how you change this function to do that. Otherwise, I'm just going to grab the operation from the head of the operations list. I'm going to take the head of the first two numbers from the top of the list. I'm going to take the tail to be the rest of that. And I'm going to take X and Y to be the first two numbers off that head that I grabbed. And now I'm just going to go through and say, look, based on the, what is it, a plus minus multiply or divide. And now I'm just going to go off and say, okay, what I'm going to do is that I'm going to go off and do this recursive call. But what I'm going to do is I'm going to say, okay, take the rest of the operations and again, put the result of adding those two numbers back on the stack with the rest of the stack, which is the tail. Same thing here, just minus or divide. And here we are doing a check that basically if y is 0, then we don't have a solution because we can't divide by 0. And we don't want to just throw an error because we need to keep going. So we have to check for that. Otherwise, we can just try to solve that this for the resulting, like I said, the rest of the operations and the result of dividing x by y with the rest of the stuff on the stack. Otherwise, if you're getting a bad operation, we're just going to return false. This should never happen. That should be a fall through. Now, the thing about it is that one of the things that when you look at this is that given the subspace, the fact that there's actually a relatively, it's not like every possible number. There's only like 25, 50, 75, and 100 are the only big numbers. And then, of course, you have 1 to 10 for what the small numbers are. It might make sense to actually try to memorize this function because there's going to be a potential, and a very good potential, for us to do the same type of computations over and over and over again. And so that's what I've done here, is that this whole operation I described is now a helper function inside this larger context. And what the larger context does is it's going to use this hash table up at the top here. And the first thing it's going to do is it's going to see if the cons of an operations and numbers, we're going to treat this operation cons number as the key. If that's in the hash table, it's going to return that, and that memo value is going to be set to that. If it doesn't find it in the hash table, it's going to return the symbol none. That's why it has this thing here. Again, if it doesn't find this key, which is this, then it's going to return this. And this is really useful because one of the things about it is that when you're doing things like hash refs, it's like, well, what if I have a hash table where I'm storing Booleans? Well, what do I want to do if I basically don't want to say that there's anything in there? That's where this gets really tricky. And this is a fairly elegant solution to doing this. It's basically no valid thing that will be in the hash table will ever have the value that's the symbol none. So I just check to see if this value is not none, that symbol, then I return back the memoized value. I've already done this computation, don't need to do it again. Otherwise, I can go ahead and then call in this helper and hand in that operations and numbers to it, and then basically hash set, which what this does is that adds a key and value pair into it. Here's the key, there's the value, and of course returns the result. Now, the interesting and important thing to note is that when we are inside this helper, we do not recurse to the helper, we recurse all the way out. And the reason we recurse all the way out is that we want the potential to basically memorize every possible computation of this. And if we just went back to helper, we would not be memoizing anything. We'd just be memoizing these very small, basically the very surface types of things, and we wouldn't be memoizing everything. So that's a very critical thing that you want to be careful about, is that you want to be able to call this larger context. And if you think about how to basically make a macro to do this, it is possible, but it is a little bit tricky because you have to do a lot of things about how to make sure that you're calling this outside function that you're memoizing. So, but this is what we've done, is we're doing this memoization. So we're not doing this computation over and over again. In this case, since these were basically add, subtract, very, very fast operations, this might not give you much. over room, but you'd be surprised at how much this would help. And what it does help us do is that it does help us to not just do these recursive calls all the time if we don't need to. So now, given this, we have all the pieces we need to solve this, basically to do this countdown solution. And so we define a function called solve that's given a target, and we're given a set of numbers. And we're not going to do anything to validate the game state here. We're just going to assume that's going to be fine. But we are going to make one assumption that we should check here, which is basically that this is basically a set of 6 numbers. 6 or less, basically. So now, what you can do here is we're going to do the following. And we're going to do let star. We're going to do length of numbers. We're going to do the result. Okay. And now we're just going to do this OR computation. And we're going to say, okay, can you solve into 1? Is it a trivial solution? For all the combination of numbers with, basically all the combination of 6 numbers that is basically too big, is there some combination of that subset that can solve it in 2, right? So if we had the target 108 and we have 100 and we have 8 in the numbers, well, 100 plus 8 solves that, so we're done. Okay. Now, what we're going to do now is we generate every possible list of 2 operations and every permutation of the subset of numbers that is of length 3. Okay. So basically every permutation of 3 numbers. And then we're going to do this. And this is where we're using the stream here. And we're using the stream here too for this 4. But here's not as obvious, but basically we are using a stream, and it's this in combinations that's the important thing. Is the in combinations function is built into Racket, and it does exactly what it does, is it creates the all combinations of this thing, which is a sequence or a list or a set, and then does basically all the combinations of that, choose 2 or choose 3, as they would say in combinatorics. So if I have 6 numbers, what's all the possible combinations of 2 numbers that are based on those 6 numbers? Here I'm doing a similar type of thing, but I'm doing this 4 star because it's nested. And what the nesting does, it says, okay, for every combination of operations, give me every combination of those numbers, give me every permutation of those numbers, because remember, ordering matters now, so we have to switch them around potentially. And that, what we do is that for every one of those combinations, if there's a solution, then we return that list of operations and the numbers that solve it. Otherwise, it's false. And then if we can't find a single one of those things in here, it will eventually fall out and return false. And what the OR part of this does, this keeps looping until the body returns something that isn't false. And so that's why this works, is that it'll keep returning false until we find a solution. And now we're doing the same thing, but now we're going to say, okay, we can go off and say, okay, and this time we do checks on the length, because we need to be able to make sure that this number actually is 4 to do this properly, or more than 4. So now we're going to say, okay, we have 3 operations, every single combination of the 3 operations, for every 4 of those X numbers, for every combination of those, for every permutation of those numbers, do this. Okay. If this is all this, then return false. We're now at 5. We do the same things. Now we have 4 operations, all the combinations there. We have all the combination of the numbers that are 5 and all the permutation of those. And if we find a solution, again, great, then return it. Otherwise, we're false. And at the very end, we have the following. For every 5 operations and every permutation of those numbers, all the numbers, because basically we're done. We have to use all the numbers to try to figure this out. If we find a solution, then return it. Otherwise, we're done. And again, we have to return the permutation, not the original numbers here, because the order of the operations and the numbers is very important here. So if it makes it all the way through this and it doesn't find anything, it will return false, saying I couldn't find a solution. And there we are. The last thing I've done as a helper is that the solution is just going to return the operations. Like I said, here's the operations, here's the numbers I did it on, as a reverse Polish notation computation. What this does is that I'm going to take that and I'm going to turn it into basically a scheme expression. And to do this, it's fairly straightforward. Basically what you have to do is I have this little helper here that takes in the operations and the numbers. If the operation is just one, I do a list of that operation and then the 2 nums, right? Otherwise, I do a list of that operation and the first number, and then recursively call that with the rest of the operations and the rest of the numbers. But the trick is to get this to work, because we're doing this in reverse Polish notation. I have to reverse the solutions list, and I have to reverse the operations list and reverse the numbers, and that will actually give me the appropriate expression. And so that's what happens when I do this here, is I turn the solution into an expression, and this is what spits out, oh, you take +8, do this, and this, and this is what gives you 315 in this case. So this is how this works. And like I said, it would not nearly be as speedy if it was trying to generate all these things. If you think about it, in something like this, that's a massive, that is a large amount of things to generate. And if you're doing a loop, you wouldn't do these things one at a time. But if you're in a functional programming language, naively you would have to, if you didn't have this string concept. And so that's why streams are so useful in a lot of programming languages. And because it allows you to have a more naturalistic expression of what you want the solution to be. And again, less imperative about how you do it, but what it is, which is basically, again, this is really what it comes down to. And here's the thing about it is that what would be a good exercise for you if you're really interested is that how you could take this, and I have basically constrained it to the space that we're in, which is basically I've said here I'm doing this up to 6, but then I'm going to give up. And then you could say, it's like, okay, well, what if I wanted to do this, that it would just recursively go off and just keep doing it until you basically, as long as this list was, keep doing it until you just ran out, and how badly could that explode on you? How many computations that could be? What would happen if you did this like with 12 numbers? Would you run out of memory? Where do you run out of memory? And this would explode on you. So you have to be kind of careful. So here I've said basically, nope, you got to do this. And you're going to have 6 numbers, and we're going to just check up to 6 and we're done. Not to do anything else. And that's the end of it. So again, but a very naturalistic, it's kind of verbose, but it's a very naturalist way of doing it. It's very inductive. You can either solve it trivially, you can solve it with any subset of 2 numbers and any given operation, or you can do this basically for any 2 operations and a list of 3 numbers from those 6 numbers, a list of 3 operations and any list of 4 numbers from those 6 numbers, any 4 operations and a list of 5 numbers from those 6 numbers, and then given all the numbers for every possible list of operations that are 5 long, then see if there's some combination of those operations that would solve it using all the numbers. And you kind of think about how as the operations grows, the combinations also kind of grow, but then they also start to shrink, right? There's way more combination of 6 numbers take 4 than there is 6 taking 5. And in this case, there's only a certain amount of permutations because we don't even have to worry about the combinations anymore. Okay. So again, I just want to have you take a look at this stuff, thinking about this, and there's a couple things that were introduced. They kind of introduced this notion of a stream, which is a way of kind of lazily introducing a sequence of numbers or values that can be very, very large by generating them once at a time. We created this context about how to do this in a sense of countdown. This basic example of an interesting numbers game that comes out from the real world. Now, there's going to be 2 things that we're going to look at later on here. Is that later on in this series, we're going to talk a little bit about constraints and how you can use constraints to solve problems in interesting ways. And you could use constraints and a constraint solver to solve this problem, as well as many related problems. And so we'll do that. But it would also be interesting to see about how much that adds to the computational overhead if you're using a constraint-based approach. The other thing about this is what's kind of interesting is that now, if I was to provide this as a solution, would this be the form I would want it to take? And the thing about it is that I thought about this, and if you think about it, is actually no. And the reason being is that we have enough structure here that we can potentially exploit. And what I mean by that is that we can take this and say, well, you know what? The solution space, the amount of possible game states. All right. Well, the list numbers we have is 6, but we're confined to stuff like that. So that isn't a massively large list. It's fairly constrained. And so what we could do that is reasonable in terms of trading off space for time is this is what we're going to do is that we could create a version of this that beforehand computes every possible solution for every possible game, right? And then store that in a file. And then basically what it would do is it would go off and look up into this file saying, oh, okay, given this game state, what are all the possible solutions? And then if that number appeared in that list, then bam, that would be, what the solution would be. So you would generate all the possible solutions and store them off in basically like a database or a spreadsheet or something like that. It'd be a very large file, but it'd be something that you could index into fairly quickly. And that would make the computation very, very fast, because literally just be a lookup into a database, so to speak. And if you're using like a website where you could have this, where the people doing this billions of times, that absolutely be the way to do it, because you would just want to be doing this lookup over and over again versus risking having to do the solution and wasting all this compute time to find out, oh, wait a minute, this is this one random case that you can't solve. And I just did all these computations, literally millions upon millions of arithmetic operations just to find out there wasn't a solution, where I could have gone off and looked up and said, oh, no, wait a minute, you gave me those 6 numbers. That's not a solution. I don't know what the solution is. So what would be a good, an interesting exercise, and I might do it myself in a stream, is to take this and see how to transform it into something that would literally generate all the possible solutions for all the combinations of game states. So anyway, thanks for watching, and I hope to see you in the next video.